Okay, problem 2.7, Griffiths 4th edition. Problem reads, find the electric field at distance z from the center of a spherical surface of radius r, shown in the figure, that carries a uniform charge density rho. Treat the case where z is less than r, so that means that's inside of the sphere, and the point outside the sphere, z greater than r. And express your answers in terms of the total charge q on the sphere. Okay, so there's a hint here. We're going to use the law of cosines to write r, script r. Okay, so remember that we are going to call this script r to differentiate this with big R and small r later. Okay, so we're going to use law of cosines to write script r in terms of capital R and theta. And be sure that to take the positive square roots if z is greater than r, but it is z minus r if r less than z. Okay, so we're going to follow those hints later. Okay, so our point is on the z-axis. Okay, so you will notice that by symmetry, the x and the y components of the electric field contributed by all dq, because this is your dq. Throughout the sphere will just cancel. Okay, so what does it mean? It means that we will only compute for the z component. So the net electric field will just be pointing along the positive z direction. Okay, and that is very important. Now, dq on the other hand, because we're looking at a spherical surface, so that means the charge is the net charge of this object, it resides on the surface. So that's why we're going to consider your charge density sigma. And from here, we can express dq to be sigma times dA. Okay? Taking note that dA for this spherical shell will be equal, which is equal to r squared sine theta d theta d phi. Okay? Okay? Now, here we have a triangle. This triangle, z capital R, r hat. So from cosine law, we can calculate r squared, this one, which is equal to capital R squared plus z squared. So the square of the other two sides of the triangle minus 2 rz cosine of the angle opposite of your script r length, theta. Okay? Okay. Now, if you're going to notice here, and also, if you want to, uh, determine the electric field created by this infinitesimal dq, this is actually pointing in this direction. So this will be your dE vector. dE vector is the electric field due to this infinitesimal dq. But we know for a fact that now that only the z component of this infinitesimal or element electric field will be considered. So that means we need to consider EZ, DEZ, which is this one. So this is DEZ. Okay, which is just a projection of DE towards the z-axis. So we can calculate that from defining this angle. Let's define this angle to be alpha. So that means this is also alpha. From cosine law, again, okay, from cosine law, r squared is equal to z squared plus script r squared minus 2z script r cosine theta. So why did I do this? Because remember that DEZ is DE cosine alpha. Sorry, this should be alpha. Okay, so we're going to use this cosine alpha to express DEZ in terms of Z, script R, and R. Okay? Okay, now let's assemble. Now, DEZ magnitude is equal to DE cosine alpha. Okay? Okay? So, so this is now equal to, okay, so this is now DE times, okay, R squared, sorry, it should be Z squared plus creep R squared minus capital R squared divided by 2Z script R. Okay? But we know that script R squared is equal to this. So this is DE times Z squared minus R squared plus R squared plus Z squared minus 2RZ cosine theta divided by 2Z script R. Okay? So from here, we can cancel R squared. And then this becomes 2Z squared. Z squared plus Z squared, so that's 2Z squared minus 2RZ cosine theta divided by 2Z script R. Okay? So we can cancel one of the Z's here. And then we can cancel the 2. So in other words, this will now be equal to DE times, so this is, sorry, DE times Z minus R cosine theta divided by script R. Okay, but what is DE? Okay, so let me allow me to move this. Allow me to move it here. Okay, so DE will now be equal to 1 over 4 pi epsilon naught times DQ divided by script R squared. But what is DQ? DQ is sigma dA. So we can rewrite this as sigma dA. Now, we can now do the integration. Okay, so right now I'm just going to set up the integration, and then I'm just going to instruct you how to do the integration, and then we'll proceed to the end result. It's a bit long, okay, and very yeah, it's a bit long. It entails a lot of steps which have been provided to you in your lecture notes as well. So anyway, so let's do this. So this now becomes integral of 1 over 4 pi epsilon naught times sigma times dA, which is r squared, times sine theta d theta d phi. This one, this one. Times, sorry, this should be z. Yeah, that should be z. So this is z minus r cosine theta divided by script r cubed. So script r squared is this one. So this is now r squared plus z squared minus 2 rz cosine theta to the 3/2. Okay, so this is now your integral. So this is a double integral in theta and phi. Okay, so you will notice that phi can be taken out. So in other words, we can separate d phi here with an integral sign. So this becomes d phi. Okay, and then we can take out this part here. And then take the sigma out, because remember that sigma is uniform. So that's a constant, as well as r squared, because r is also a constant. So now we are now left with this integral. Okay, now the limits of integration for phi, because we are going to look at the whole sphere. So phi would be from 0 to 2 pi. So this is the easiest part of this integration. This is just equal to 2 pi. But the hard part is this part. So this is 0 to pi. Okay, so let me just rearrange this to have a better view. Okay, so this is now your integral. Okay, so this is a lot of steps. So first is you're going to integrate by letting u by letting u equal to cosine theta and du to be negative sine theta d theta. Then your limits of integration will be difference. Okay, so okay. So let me just clear this thing here. So this becomes 2 pi. Yeah. So now that is much clearer. So anyway, so the details of the math, which is not my concern right now, because you can do the integration by yourself. But the point is that the end results. The end result here is easy, is now equal to the following. Okay, so yes, you can actually cancel 2 pi with 4 pi, but usually I just maintain this 1 over 4 pi epsilon naught to be separate. So this is 1 over 4 pi epsilon naught. And then the result would be 2 pi sigma r squared divided by c squared times z minus r over z minus r absolute value, because we're looking at this positive square roots, then minus negative z minus r over z plus r. Okay, so this is now the electric field. Okay. Okay, so this is now the electric field. Okay, of course, we want to express your answers in terms of the total charge on the sphere. And what is the total charge on the sphere? So remember that sigma is your surface charge density. So that's Q over the total surface area of the sphere, wherein in this case, this area would be 4 pi r squared. So therefore, Q will now be equal to sigma times 4 pi r squared. Okay, so now we can rewrite this as follows. So this, because this is 2 pi sigma r squared, so that means we have 2 divide 2 here, and then this becomes 4 pi r squared sigma, so this becomes Q. Okay. Now, let me go to our special cases. Now, let's say for outside the sphere, z greater than r, okay, for z greater than r, so EZ becomes this one. Okay, so again, this is 1 over 4 pi epsilon naught times Q over 2z squared. Now for z greater than r, so this is z minus r. This is 0. Sorry, this is yeah, this becomes negative z plus r divided by r. So this becomes 1. This becomes plus 1. And this is 1. Okay, so that's 1 plus 1 equals 2. So that means it's now equal to this one. So what do you notice here? This is just like a point charge. So that's 1 over 4 pi epsilon naught times Q over z squared, where z is the distance of your points from your charge. Now, how about inside? For charge, for z less than r. So again, EZ equals 1 over 4 pi epsilon naught Q over 2 z squared. Now, what happens here? If z is less than r, this should be negative 1 minus negative 1. So that is 0. So that means the electric field inside of that sphere is 0. So if you're going to put a test charge inside the sphere, that test charge will not experience an electrostatic force. So that means it will not move, or it will just float. That charge will just float inside the sphere. Whereas if you place let's say a charge outside, that charge will experience an electric force because of the electric field created by your charge, or of your sphere. Okay, so this is now the result of problem 2.7 of Griffiths 4th edition.